All right, everyone, we are back, and we are going to be looking at our question 2, 3-point bending stress at fracture. So we have the following fundamental equation here. We're given the equation information. Instron, 50 kilonewton load cell. This is our resolution, so there's some uncertainty in our force. So this is going to be our uncertainty in the force. Being measured with a ruler, so there's going to be some uncertainty in L, which is equal to uncertainty in B, which is equal to the uncertainty in D, which is going to be equal 1 times 10 to the minus 2 meters. Force is measured, so there's going to be precision error in the force, precision error in the width of the beam B, and a precision error in the length. Let's see, width of the beam is measured, average length. The nominal value of the thickness was this, so we just have nominal value. Determine the uncertainty, what contributes most. We know the drill. So let's go ahead. We're going to clear our kernel. Let's go ahead and start to solve this problem. So we have some fundamental expressions. So sig F equals 3 times F times L divided by 2 times B times D squared. I have some uncertainty in my force, which is going to be equal to 10 times 10 to the minus 3 newtons. I have some uncertainty in my L, which is equal to 1 times 10 to the minus 2. That's uncertainty in B is equal to uncertainty in L. Uncertainty in D is equal to uncertainty in L. We also have number of force, which is equal to 48. I have a x bar F, which is equal to 120 times 10 to the third. We have a SF, which is going to be equal to 4.7 times 10 to the 3. We have the width of the beam was measured, so number of B width is equal to 14. X bar B is equal to 17 times 10 to the minus 2. SB is equal to 3 times 10 to the minus 3 millimeters. Excellent. And then NL is equal to 23. XL is equal to 2.7. And SL is equal to 0.2. There we go. So when we have all, and we also need to do our partial derivatives. So we have uncertainty in everything. So d sig df equals derivative sig f with respect to f. And we'll just copy this and we'll get all the rest of them. So it's partial derivatives. F, L, B, D. F, L, change it to L, capital L, B, and D. There we go. Okay, so the other thing is I'm going to need the t value. Here we're looking at a 10% significance, so I need a t of 0.05, and then we're going to have 3 separate n's. So what I'm going to have to do, hopefully it's in here. F table. No t table here. All right, that's okay. But we're going to have to go and find our t table. Ooh, that's lecture 8. Instead, maybe lecture 5. All right, so I'm going to go ahead and write these values down here quickly. Because we need t of 05 infinity, so t 05 inf equals 1.645. That will be for our number of force measurements. We need T0513, which is going to be equal to T0513, 1.771. And then finally T05 T.05, T05, and then what's our new for the other one? 22, T05, 22, 1.717. There we go. So we can now go ahead and let's go ahead and actually solve the rest of this problem. So my bias B sig F is going to be equal to square root, and then I need to put, for example, I need to do my d sig df times uncertainty in F divided by sig F, and we're going to do that squared, plus, we're going to copy and paste that for all the variables. So F, L, B, D. Yep, F, L, B, D. F, L, B, D. Okay, excellent. F, L, uncertainty in L, dB, uncertainty in B, uncertainty in D, dB, D. Here we go. So, and then we need to replace slash dot. B goes to X bar B. D goes to, in the problem statement, I believe that we're told that the nominal thickness is 4.5 centimeters. So that's going to be 4.5 times 10 to the minus 2. F goes to X bar F, and L goes to X bar. Or did we give an X bar L? Or X, I think we just did XL. 2.7 meters. Oof, that's a large error. We'll come back to that. That's probably got mostly to do with that millinewtons. But anyways, let's go through here now. So let's do precision error in F. Precision error in F is equal to T05 inf times S of F divided by square root of NF. Yep, and then we're going to do all of this divided by our X bar F divided. And then we'll do the same thing here, but now we'll go through PF. Now instead of PF, let's do PB. B, how many measurements did we have? T05, 13. B and B, X bar B, and then finally L. L, T05, L, we had 22 measurements. SL and L, and then X. Yeah. All right, and then finally, the total uncertainty, sig F, equals square root of B sig F squared plus PF squared plus PB squared plus PL squared. There you go. Obviously, most of it's in your sig F. Lots of ways that we can kind of improve that. Obviously, you can change essentially that load cell uncertainty. That centimeter uncertainty is pretty bad, so you can significantly change that. And yeah, that's pretty much it. Fantastic. See you next time.